Welcome to this explainer. Today, we're actually going to play Cosmic Detective to uncover a truly bizarre astronomical mystery hidden deep in the universe. We're looking at a fascinating case of stolen identity, hidden siblings, and literal stellar destruction, all wrapped up in one massive astrophysical puzzle. I want you to picture something for a second. Imagine peering into a dense stellar graveyard. We're looking at the core of a core-collapsed globular cluster, which is essentially a place where hundreds of thousands of ancient stars are packed incredibly, uncomfortably close together. The extreme gravity and intense radiation in these chaotic environments forge some of the most unusual objects in existence. It's basically the ultimate hiding place for cosmic anomalies. So, to get our bearings, our actual crime scene is located a staggering 8,000 light-years away from Earth, right in the Amara constellation. This is Caldwell 86, also known to astronomers as NGC 6397. It happens to be one of the closest core-collapsed globular clusters to our solar system, which makes it the absolute perfect laboratory for high-resolution telescopes to try and untangle all that chaos within. Just look at this stunning view from the Chandra X-ray Observatory. The core of Caldwell 86 is incredibly crowded. Each of those distinct red circles you're seeing, that represents a separate X-ray source. In a packed environment like this, stars are constantly interacting, colliding, and capturing each other to create these totally exotic binary systems. And all this chaotic, dense material serves as the perfect hiding spot, completely masking the signals of objects that, frankly, don't want to be found. Let's dive right into Section 1, the first bizarre discovery, Pulsar A. Way back in 2001, astronomers stumbled on an X-ray source, here designated as U12. Officially, it's known as PSR J1740-5340, but we're just going to call it Pulsar A. Right away, it was an oddity. It's a rapidly spinning neutron star completing a full rotation every 3.65 milliseconds. Think about that. It's spinning hundreds of times a second. It's locked in a short 1.35-day orbit with this bloated companion star that's roughly 0.19 times the mass of our sun. But here is the really strange part. When astronomers pointed radio telescopes at it, its signal completely disappeared, or eclipsed, for nearly half of its entire orbit. It just vanished. To understand why it vanishes like that, we have to talk about a really cool classification. Pulsar A is what we call a redback pulsar. Astronomers playfully named these systems after the venomous Australian redback spider. You know, the relative of the black widow that famously destroys its mate? Well, in this cosmic version, the energetic pulsar is just blasting its larger companion star with this relentless wind, slowly stripping away its atmosphere and basically destroying it. Which leads us perfectly into Section 2, hunting the hidden sibling, and the mystery of U18. For years, astronomers had this sneaking suspicion that Pulsar A wasn't the only redback in the cluster. They kept a close eye on a nearby source designated as U18. And the clues really started to pile up when they looked at U18 through the Hubble Space Telescope. By studying its optical light, they realized the star was varying in brightness every 1.96 days. But not just that, it was glowing with this intensely anomalous blue light. A standard star of its size and temperature absolutely should not be glowing that blue. This was a massive hint that some unseen power source was literally cooking one side of the star. So, they did what any good detective would do. They cross-referenced the data. By matching Hubble's optical view with Chandra's X-ray vision, the pieces finally started to fall into place. U18 wasn't just emitting soft thermal heat. It was emitting hard, non-thermal X-ray radiation. That is a very specific type of emission that is virtually identical to our known redback pulsar A. It strongly suggested that a violent collision of particles was happening right there in the system. But this brings us to a huge contradiction. If U18 is a twin to Pulsar A, if it's just another rapidly spinning neutron star blasting its companion, why in the world did it evade radio detection for nearly 2 decades? I mean, how can an object be so blindingly bright in X-rays, yet completely, stubbornly silent to our most sensitive radio dishes on Earth? Let's find out in Section 3, Unmasking Pulsar B, and the big radio reveal. To finally solve this, astronomers had to push the absolute limits of radio astronomy using the Parkes radio telescope and the Meerkat array, and they did it. They finally found the hidden sibling, PSR J1740-5340b, or Pulsar B. And the reason it hid for so long is truly staggering. The radio silence wasn't because the pulsar was turned off.
No, it was because the entire system was choking on its own debris. The companion star is shedding such a massive, thick envelope of ionized gas that the pulsar's radio signal gets completely absorbed. When reviewing the data, they realized Pulsar B remained entirely undetectable in radio waves for 14 continuous months at one point. It's practically in perpetual stealth mode. And when you actually lay the stats out side by side, it brilliantly illustrates just how extreme these twin systems are. Pulsar B spins every 5.78 milliseconds. But check out that orbital period, 1.97 days. That makes Pulsar B the longest period eclipsing binary pulsar currently known in any globular cluster. It's got a slightly heavier companion too, around 0.27 solar masses, and it's exactly this wider orbit that allows such a massive obscuring cloud of material to build up between the stars. Now for Section 4, the anatomy of cosmic shocks, and how these redbacks actually eclipse. So why do these stars eclipse at all? And what creates those anomalous blue lights and hard X-rays? Well, it all comes down to a clash of cosmic titans happening 8,000 light-years away. Step 1. The pulsar acts like an absolute powerhouse, firing off a relativistic wind of high-energy particles. Step 2. The companion star, which is getting weakened by the pulsar's intense radiation, swells up and sheds a massive envelope of ionized gas. It's literally bleeding its atmosphere into space. And Step 3. When that pulsar wind slams into the wall of infalling gas, it creates this violent intra-binary shock front. This shock acts like a giant particle accelerator. It generates the intense X-rays we see and completely blocks the radio waves from escaping. I absolutely love this quote from the original 2001 study on Pulsar A because it perfectly captures the reality for both of these systems. The pulsar isn't just orbiting near its companion. It is literally swimming through the destroyed remains of its partner's atmosphere. It is plowing through a thick, turbulent cloud of ionized plasma. And that's exactly why the radio signals get delayed, scattered, or just completely erased from our view, depending on exactly where the pulsar is in its orbit. Which brings us to Section 5, the fate of redbacks, the big picture. So you might be wondering, why dedicate decades of telescope time just to find a pulsar that actively hides from us? Well, finding redbacks like Pulsar B fills a really vital gap in our understanding of stellar evolution. See, we know that old dead neutron stars get spun up to millisecond speeds by stealing matter from a companion star. But the transition from an accreting X-ray binary to a clean, normal millisecond pulsar, it's messy. Redbacks are that messy, crucial missing link. By unmasking these hidden systems, astronomers can finally piece together the full evolutionary life cycle of neutron stars. We could finally figure out if they eventually evaporate their companions entirely to become lonely black widow pulsars, or if they follow a completely different path. I want to leave you all with this provocative thought. Pulsar B was sitting right there in the X-ray data of Caldwell 86 for 2 whole decades. It was hiding in plain sight behind a wall of its own making. It took immense patience and cross-referencing multiple wavelengths of light to finally unmask it. It really makes you wonder, as we look deeper into the dense, chaotic cores of globular clusters across our universe, just how many other extreme cosmic monsters are still out there, silently lurking in the dark, just waiting to be found. Thanks for joining me on this explainer. Keep looking up.